When we had when I introduced the product rule, it was written as the probability of an intersection of two events, the probability of E intersect F, was equal to the probability of the first event times the probability of the second event given the first. If we took and divide both sides of this equation by the probability of E, so if I took and divided both sides of this by the probability of E, like that, I end up getting this equation. So it's just a little algebraic manipulation here. This is to say that if we were trying to find the probability of F given E, it's this thing. Actually, we saw this when I first introduced the conditional probability. I gave this exact formula. But you can see this formula and the conditional or the product rule are the same formula. They're just slight manipulation. All right, so Bayes' theorem is what we get when we consider taking this and applying it to a tree diagram. So kind of the simple case, the way that we're going to be seeing this in this class, one of the ways we're going to be seeing it at least, the simple way we're going to be seeing it, I should say, is if we had, if we're trying to find the probability of F given E. So this, in this example, we have E being the first event and F being the second event. If we're trying to find the probability of F given E, this is, oh no, I think I had that backwards. Yes, I do have that backwards. I'm trying to find the probability of F given E. If F was the first event and E was the second event, there we go, then it's not exactly straightforward. But if we use this rule, the probability of F intersect E, that's this branch right here, and divide by the probability of E, well, we'd have to use the law of total probability here to find the probability of E. We would take whatever this branch is and add it to that branch. That, through the law of total probability, we'd take this number divided by the sum of those two. That would give us this formula. That's all this big ugly formula here that we call Bayes' theorem. That's all it's doing, except instead of circling this branch probability, it's saying take this probability times this probability. Take the product of those. That's going to give us this thing up here. That's the top part here. Probability of F times the probability of E given F. That's that number. And then take that number plus this one down here. So this is that same thing we just saw up there, plus that one down there. That's this number times that one. Multiply those together, it gives us this branch probability. That gives us our denominator. So this is really just taking this initial conditional probability formula and kind of applying it to a tree diagram. That's all Bayes' theorem is doing. So let's just see some examples. You're playing a game that starts by rolling a six-sided die. We've seen one of these similar to this already. On a roll of 1 or 2, you draw from the first cup. On a draw of 3 through 6, you draw from the second. The first cup has 1 red marble and 4 green marbles. The second has 3 and 2, respectively. First off, let's construct a tree diagram so we can get a good view of this overall problem. So we have 2 cups. Let's say cup 1 and cup 2. The probability that we're going to be drawing from cup 1, well, we could draw from cup 1 on a 1 or 2, so this would be 2 out of 6. The probability of drawing from cup 2, which actually, since there's only 2 cups here, we could call it cup and the complement, or you could call it a couple of different things. I'm going to go ahead and stick with C and C complement here. So this is drawing from the second cup, that's drawing from the first cup. We end up getting 4 out of 6 here. Alright, the probability of getting a red marble, given that we're drawing from the first cup, well, let's see, the first cup has 1 red marble and 4 green marbles. This would be 1 out of 4. The probability of drawing something other than a red marble, given that we're drawing from the first cup, would be 4 out of 5. I don't know why I said 1 out of 4. It should be 1 out of 5. There we go. The second cup, if we're down here, I want to also look at the probability of getting a red marble, given that we're drawing from the second cup. Let's see, the second cup has 3 and 2, so this would be 3 out of 5. And the probability of drawing something other than a red marble, given that we're drawing something out other than the first cup, or the second cup in other words, is 2 out of 5. Okay. So we can figure out these branch probabilities. Here we get 2 out of 30. This is this number times that number. 2 out of 6 times 4 out of 5 is 8 out of 30. 4 out of 6 times 3 out of 5 is 12 out of 30. And 4 out of 6 times 2 out of 5 is 8 out of 30. In total, these should sum up to 1, so you can kind of double check to see if you made mistakes if you do the entire problem like this. Let's figure out, okay, let's use the law of total probability to determine the probability that I draw a red marble. So here and here, these are the two branches where we drew a red marble. You can see there's a red and a red there. Those are the two where we drew a red marble. So that would be 2 out of 30 plus 12 out of 30, giving us 14 out of 30. That would be the probability of drawing a red marble, just in general in this game. So your friend just played the game and got a red marble. Let's use this to determine, given that knowledge, what is the probability that they drew from the first cup? Well, you can already see the probability of getting a red marble from the first cup is rather low. The probability of getting a red marble from the second cup is actually quite a bit higher. So the probability of drawing a red marble, the probability of drawing from the first cup, given that it was a red marble, is going to be this number divided by the sum of these two. So we're going to do 2 out of 30 divided by 2 out of 30 plus 12 out of 30. So this one right here, this again was that total probability. That's that 14 out of 30 that I just wrote down up here. And fortunately, when we're dealing, if we keep all these denominators the same, 2 out of 30 divided by 14 out of 30, remember when you're dealing with fractions, you can take and multiply both the top and the bottom by whatever number you'd like, just like you can divide the top and bottom by whatever number you'd like. Well, if I take and multiply both the top and the bottom by 30, it gets rid of those. And I end up with 2 out of 14, which I could reduce down to 1 out of 7. So that means the probability that they drew from the first cup, given that they got a red marble, would be 1 out of 7 using Bayes' theorem.